Our next unit is on something known as electrochemistry. So electrochemistry studies changes caused by electricity and also with the production of electricity. So we have two different situations, two different reactions that occur. One that needs electricity to occur, and then the other that produces electricity. So these reactions occur in two different types of electrochemical cells. One of them is known as an electrolytic cell. And in an electrolytic cell, electrical energy from an external source, such as a battery, causes a non-spontaneous redox reaction to occur. So the reactions that occur in electrochemical cells are redox reactions. We'll review what that means in just a bit. Just know that in an electrolytic cell, the reaction is non-spontaneous, and therefore you need an external power supply to make that reaction occur. The other type of electrochemical cell is known as a voltaic or galvanic cell. And in this type of electrochemical cell, electrical energy is produced from a spontaneous redox reaction. So a reaction occurs spontaneously, and that reaction is able to generate electricity. Ionic and electrolytic conduction occurs when electrical current is conducted due to the motion of ions in a liquid or solution. So in a solution, we have individual ions. They're able to move around within that solution. In, say, a molten, melted, that means molten ionic compound, also have mobile charged particles that are able to move around. And we have conduction that occurs because of this. You can see that on page 793 at the top. We have charged particles moving within that substance to the positive and negative things. I don't want to tell you what they are just yet, but just know that those charged particles are able to move around inside that solution or molten compound, whatever it may be. All right, so let's review redox. Redox, of course, is short for reduction and oxidation. Reduction is a process where electrons are gained. Those substances that are reduced gain electrons from substances that are being oxidized. So oxidation is a process where electrons are lost. Cannot have something gain electrons without something else losing electrons. So these two processes occur together. One way to remember which is which, we have a couple things here. Leo the lion says Gur. Losing electrons is oxidation. Gaining electrons is reduction. The other one that you may have seen is oil rig. Oxidation is losing electrons. Reduction is gaining electrons. Really don't care which one you use, as long as you know the difference between oxidation and reduction. Some terms that often trip students up: oxidizing agent and reducing agent. We'll start with reducing agents. This is a substance that causes something else to be reduced. It's causing something else to gain electrons, while at the same time it is losing electrons, or it is being oxidized. Conversely, the oxidizing agent is the substance that causes something else to be oxidized. It causes something else to lose electrons, while at the same time it is gaining those electrons, or it is being reduced. In fact, the reactants of a redox reaction are these two substances. We refer to the reactants as the oxidizing agent and reducing agent. And we'll talk about that with redox titrations, where one chemical is the oxidizing agent and the other is the reducing agent, and those are the things that are reacting with each other. All right, some more terminology. The electrodes, these are the things that are attached with wires to one of two things, depending on the type of electrochemical cell. If it's an electrolytic cell, it's attached to a battery. These things are attached to a battery. And if it is a galvanic cell, then the electrodes are the things attached to the measuring device, the voltmeter or the ammeter. So it says here that the electrodes are the surfaces or locations where the redox reactions occur. Now, especially with electrolytic cells, the electrodes themselves are not involved in the redox reaction. And so because of that, we use electrodes that are inert. Inerts meaning they don't react, they are not involved in the reaction. So some common inert electrodes that we'll see in electrolytic cells are things like graphite or platinum or palladium. So if you see those, chances are it's an electrolytic cell. Those substances themselves are not involved in the reaction. The electrodes have names depending on what is happening. We have cathode and anode are the types of electrodes in an electrochemical cell. Now, they have some similarities, but they have some differences in terms of the electrodes in an electrolytic versus a galvanic cell. So let's start with the cathode. The cathode is the electrode where reduction occurs. Now be careful, it's not necessarily the substance that is being reduced, but it is where reduction is occurring. What's similar in an electrolytic and galvanic cell is that the cathode is the electrode where reduction occurs. What is different about the cathode in an electrolytic and galvanic cell are their charges. So in a galvanic cell, the cathode carries a positive charge, and in an electrolytic cell, the cathode carries a negative charge. Anode, of course, is going to be the opposite then. The anode is the electrode, either in an electrolytic or galvanic cell, where oxidation occurs. Again, this anode, this substance, may or may not be the substance that is being oxidized, but it's definitely where the oxidation process occurs. This is the negative electrode in a galvanic cell, and it is the positive electrode in an electrolytic cell. So some other things that may help you to remember what's going on during a redox reaction. Red Cat, your book uses. So reduction occurs at the cathode. So that's something to help you remember that. And then we'll be talking a lot about vowels and consonants. So in terms of, where reduction occurring, where oxidation is occurring, all kinds of stuff we can use vowels and consonants to help us understand what's going on. The rest of this lesson will focus on electrolytic cells, and we'll look at a couple different examples. Remember, non-spontaneous chemical reactions do not occur by themselves. So they are forced to occur, in this case by an input of electrical energy. This process where we use electricity to make a non-spontaneous redox reaction occur is called electrolysis. And as I mentioned before, in electrolytic cells, we often use inert electrodes. So you have a diagram in your book at the top of page 793 and some other pages as well. And then here's just a typical electrolytic cell. We have two inert electrodes. Whoops, I don't want to do it like that. Let's try again. Two inert electrodes here. So they could be platinum or graphite. They're connected to a power supply. In this case, this has a battery. And the electrode on the left is the electrode where oxidation is occurring. So this is the anode. And then the electrode on the right is where the reduction is occurring. And this, of course, is a cathode. And these electrodes can be in one of two things. And we're going to look at examples of each. Electrolysis of an aqueous solution, as well as electrolysis of a molten ionic compound. Let's start with the electrolysis of molten sodium chloride. So it says in this, molten sodium chloride is electrolyzed. So now something that's important to understand is the composition of what you are working with. So first of all, it says it must be melted, the sodium chloride must be melted so that electricity can be conducted by mobile ions. Remember, as a solid, those ions are not mobile, they're not able to move around very much. So we need to melt this substance. For sodium chloride, it will melt at a temperature above 801 degrees Celsius. You don't need to know that. Just know that it's got to be really hot and liquid form in order for electrolysis to occur. Something that is really, really, really important is that there's no water present. So sometimes we'll see in our next example that water can be involved in the redox reaction. Here, all we have is, and I'm going to show it together because remember, in a liquid, the ions are not separated from one another, but they are able to move around. And so we have sodium ions and chloride ions all sliding past one another in this liquid compound. All right, here's a simplified diagram of the down cell. There's also a picture in your textbook, page 794, actual down cell on the right, and then just a representation of a down cell on the left. And so we have our molten sodium chloride. Something to keep in mind is all we have is Na plus and Cl minus. Well, what's going to happen to the Na plus? What's going to happen to the Cl minus? Now, it says Cl bubbles, that's technically Cl2, right? So we have chlorine gas that's forming on one electrode, and then we actually have sodium metal forming on the other electrode. So notice that the electrons are going in this direction through the wires. The electrons in an electrolytic cell always go towards the substance that is being reduced. So there we go with our consonants. Towards the substance being reduced. Or the electrons go away from what's being oxidized. Remember, when a substance is oxidized, it's losing electrons. So the electrons go away from that substance. All right, so what happens here? I kind of already talked about it. Pale green gas. So let's say you're actually set this up and you take some molten sodium chloride, stick a couple graphite or platinum electrodes in it, attach that to a power supply. What would happen? What you would see is that one electrode, one of the electrodes, a pale greenish yellow gas would form. This greenish yellow gas is chlorine. And then on the other electrode, we would see a silvery liquid, because it's hot in there. So silvery liquid would form on the other electrode. So question is, where did the chlorine gas come from exactly? How did it form? And where did the sodium metal come from? Remember, think about what's the composition of that substance is. We have molten sodium chloride. So let's interpret the results here. So let's start off with the cathode half reaction. Remember, at the cathode, reduction occurs. And so something is being reduced. Something is gaining electrons. Well, let's try this. Can chloride ions gain electrons? So remember, when we write a reduction half reaction, the electrons that are being gained go on the left side. These are known as half reactions because they are half of the overall process. No such thing as just a reduction half reaction. No such thing as just an oxidation. They occur together, but we can write them separately. So back to this. Can chloride, I should say, be reduced? If chloride were reduced by gaining one electron, we would make Cl minus 2. Pretty sure that's chlorine does not have an oxidation state of -2. So it's not the chloride that is being reduced, but rather it is the sodium ions that are being reduced. So let's write that half reaction. So we have sodium ions that will gain one electron. When the sodium ions gain one electron, you form sodium metal. At the other electrode, the anode, is where oxidation occurs, so something is losing electrons. Can sodium ions lose electrons? Well, if sodium ions lose, it's not an arrow there too. If sodium ions lost electrons, you would make Na plus 2. Pretty sure that sodium does not form an oxidation state. Plus 2, so it's not the sodium that is being oxidized. It must be the chloride ions. So when chloride loses an electron, you form chlorine. Technically, we said you're making chlorine gas. That's one of the observations. And so we want to make sure that our half reactions are balanced. And so 2 chloride ions will be oxidized to form 1 molecule of chlorine. So, like I said before, you cannot have something being oxidized without something else being reduced. So let's come up with the overall equation. We simply take the sum of the oxidation and reduction half reactions. Something to be careful of, though, is this. Does this make sense to have 1 electron gained and 2 electrons lost? No, the number of electrons gained and lost in a redox reaction must be the same. So let's go ahead and multiply this top half reaction by 2 so that we have 2 moles of electrons gained, which is equal to the 2 moles of electrons lost. And then we combine our half reactions. Ultimately, we end up with this. And that is our overall equation for the reaction. 2 sodium ions and 2 chloride ions react essentially to form 2 atoms, I guess we will, of sodium and 1 molecule of chlorine. So in this electrochemical cell, electrons are forced through the cell by the DC current, direct current, technically there, from the battery. Don't have to worry about what that means exactly. And the electrons are going from the anode to the cathode. Charge of the electrodes, again, we talked about this before. In an electrolytic cell, the cathode is the negative electrode and the anode is the positive electrode. And as mentioned before, there's an actual diagram of an actual down cell on page 794 in letter B. Let's look at a different situation. So this time, let's look at the electrolysis of aqueous sodium chloride. Now, again, let's think about the composition of this solution. What exactly is in a solution of sodium chloride? You have sodium ions, you have chloride ions, and I'm pretty sure there's another very large component of that solution, that component being water. Now, as I mentioned before, sometimes water is involved in the reaction. And so we got to check this out and see, okay, what's going on? So this time, you take an aqueous solution of sodium chloride, stick a couple electrodes in it, hook that up to a battery, and a redox reaction occurs. So what are the observations here? This time we see that a colorless gas is produced at one electrode, that colorless gas being hydrogen. And interestingly, the solution around this electrode becomes basic. So if you had, say, maybe solution of sodium chloride, puts a couple drops of phenolphthalein in there, the solution around that electrode where the colorless gas is being produced would become basic, and we would see pink because of the phenolphthalein. And on the other side, the other electrode, we have a pale greenish yellow gas that is being produced. So what is going on? We know where this is coming from, but where is that coming from? And why is it that and not this? Well, we have some other considerations. All right. So we know that the chlorine gas is coming from the oxidation of chloride. So let's once again write that equation, and we'll have that balance this time ready to go. Make Cl2 plus a loss of 2 electrons. However, we don't make Na sodium metal this time. Why not? Well, it just so happens that the H plus ions in water, or the hydrogen, technically it's just the hydrogen in water. The hydrogen in water is more easily reduced than sodium ions are. So instead of producing sodium metal, we get hydrogen gas at the cathode. The solution becomes more basic because of the production of hydroxide ions in the cathode half reaction. So let's go back and write the cathode half reaction. Sorry, I didn't have a space for this in the notes. So cathode half reaction looks like this. And I believe this half reaction is given to you on your table of reduction potential, so you'll want to confirm that and make sure it's there. So there should be one equation for the reduction of water, and when water is reduced, technically it's the hydrogen in water that's reduced to hydrogen gas, and this reaction also produces hydroxide ions. There's another equation that shows the oxidation of water. In that case, it would be technically the oxidation of oxygen to oxygen gas, and then that reaction actually produces hydrogen ions, as we'll see later. All right, so back to this, solution becomes basic because the hydroxide ions are produced in that half reaction. Letter C is not correct there. That's for a different one. Let me get rid of that. So let's once again take our two half reaction and combine them. Here is our reduction half reaction. Oops, that's two waters there. Sorry about that. And then our oxidation half reaction. Looks good. We got 2 electrons gained, 2 electrons lost. We don't need to mess with either of those half reactions. Let's cancel those. And here's what we end up with. And that's the balanced redox equation for the electrolysis of molten sodium chloride. So once again, charges of the electrodes, the cathode is negative and the anode is positive. We can see a diagram of this, again, also in your book on page 796. I apologize, I don't have this next section typed up in my notes, so I'm just going to read it to you. Next one, we have electrolysis of aqueous sodium sulfate. So again, just like last time, we want to look at the composition of this solution. So what is in this solution? We have sodium ions, sulfate ions, and once again, water. So what happens? Take this solution, stick a couple electrodes in it, hook it up to a battery. Here's what we see. Letter A says hydrogen gas is produced at one electrode, and the solution around this electrode becomes basic. Well, that sounds familiar. However, this time, on the other electrode, we see that oxygen gas is produced, and the solution around that electrode becomes acidic. So what's going on here? So once again, the hydrogen in water is more easily reduced than the sodium ions are, and that's why we make hydrogen gas instead of sodium metal. So once again, that half reaction looks like this, same as what we saw before. So we have the reduction of water, technically the hydrogen in water. Whoops, that's 2 hydroxides. And our hydrogen gas comes from there. Well, how about the oxygen? Where does the oxygen gas come from? Well, must come from the water. So it says the oxygen in water is more easily oxidized than sulfate ions are. So we make oxygen gas at the anode. So here is the equation for the oxidation of water. Again, hopefully this is also in your table of reduction potentials. And we see that you produce not only oxygen gas, but H plus ions, and that is why the solution becomes acidic. Now there's a picture of this diagram, page 797 in your textbook at the top, electrolysis of aqueous sodium sulfate. So how do you know? Are you supposed to know which substance is more easily oxidized or more easily reduced? Yes, but not yet. So I'll teach you how to use your table of reduction potentials to predict which substance is more likely to be oxidized and reduced. With these examples, we're using our observations, those observations that were given to you. You make hydrogen gas, so that must mean that the water is being reduced. Technically, the hydrogen in water is being reduced. And then you're also given the observation that oxygen gas is being produced. This is through the oxidation of water, technically the oxidation of the oxygen in water. All right, that concludes our lesson on electrolysis. Thanks for watching.